Good morning, everyone. Welcome to the session on statistical physics for the BSc Physics students. Today, in this session, we are going to discuss about Bose-Einstein statistics. We have already known the statistical mechanics can be divided into two main classes. They are classical statistics and quantum statistics. Classical statistics are Maxwell-Boltzmann statistics interpreted successfully many ordinarily observed phenomena such as temperature, pressure, energy, etc. But it failed to account for several other experimentally observed phenomena such as blackbody radiation, photoelectric effect, specific heat capacity at low temperatures, etc. This failure of classical statistics forced the issue in favor of the new quantum idea of discrete exchange of energy between the systems. Thus, a new quantum statistics was investigated. There are two types of quantum statistics: Bose-Einstein statistics and Fermi-Dirac statistics. Particularly in this session, we will see about Bose-Einstein statistics. First, let's have a look to the basic postulates of these Bose-Einstein statistics. Bose-Einstein statistics is applicable to the particles with integral spin angular momentum in units of h by 2 pi, where h is the Planck's constant. All particles which obey Bose-Einstein statistics are known as bosons. The examples for these bosons are helium atoms at low temperature and photons. Any number of particles can occupy a single cell in phase space. The size of a cell cannot be made less than h cube, where h is the Planck's constant. The number of phase space cell is comparable with the number of particles. Therefore, the occupation index is equal to Ni by Gi is equal to 1. The total number of particles in the system remains constant, that is, summation over delta Ni is equal to 0. The total energy of the system also remains constant, therefore summation over Ei into delta Ni is equal to 0. Statistical mechanics is concerned with the properties of matter in equilibrium, so our aim is to find the most probable state or equilibrium state of the system. The most probable state of a system is that macro state which has the maximum probability of occurrence. The procedure for determining this most probable statistical distribution involves two steps. They are obtaining the number of distinguishable arrangements which gives rise to the same distribution and maximizing the number of arrangements with respect to different distributions. We will see the Bose-Einstein distribution law. For an assembly of n bosons, the actual number of ways in which Ni particles are to be distributed in Gi sublevels is given by Ni plus Gi minus 1 factorial whole divided by Ni factorial into Gi minus 1 factorial. The total number of distinguishable and distinct ways of arranging n particles in all the available energy states is given by Wi is equal to capital Pi of Ni plus Gi minus 1 factorial whole divided by Ni factorial into Gi minus 1 factorial, where the capital for large values of Ni and Gi's we can neglect this 1 in this equation. So for the most probable microstate is given by Wi is equal to capital Pi of Ni plus Gi factorial whole divided by Ni factorial into gi factorial. Our next aim is to maximizing this most probable microstate. So taking natural logarithm on both sides of this equation, we will get ln w is equal to summation over ln of ni plus gi factorial minus ln ni factorial minus ln gi factorial. As ni and ji are large numbers, we can use Stirling's approximation. This says that for large value of n, we can write ln n factorial is equal to n into ln n minus n. Use this Stirling's approximation to this equation, we will get ln w is equal to summation over ni plus gi into ln of ni plus gi minus ni into ln ni minus gi into ln gi. For the most probable distribution, delta ln w max is equal to 0. Therefore, differentiating that ln w equation, we will get delta of ln w max is equal to summation of delta ni into ln ni plus gi plus ni plus gi into 1 by ni plus gi into delta ni minus delta ni into ln ni minus ni into 1 by ni into delta ni, that is equal to 0. By using the method of Lagrange's undetermined multipliers, we will get ni is equal to gi divided by e to the power of alpha into e to the power of ei by kt minus 1, where alpha is the Lagrange undetermined multiplier and k is the Boltzmann constant and capital T is the absolute temperature. This is known as Bose-Einstein distribution law. We will see the next Bose-Einstein distribution function. The energy distribution function f of ei is the average number of particles per quantum state in the ith energy level ei. It is given by f of ei is equal to ni divided by gi, that is equal to 1 divided by e to the power of alpha into e to the power of ei by kt minus 1. So in this session, we have learnt the need of Bose-Einstein statistics and Bose-Einstein distribution law, Bose-Einstein distribution function. Thank you for watching the video. Have a nice day.